now we are ready to apply KVL and KCL for the delta Z equivalent circuit that we spoke about earlier, delta R, delta L, delta G, delta C on an interval delta Z of the transmission line. Here we do time domain and frequency domain analyses for more exposure and better understanding. In the voltage expression here in the time domain we use lowercase. The voltage expression here we use uppercase. Similarly for the current, we write simply that the voltage here is equal to this voltage plus that voltage, and the current here is equal to this current here plus that current, the branching of this node here. So we write those expressions, KVL and KCL, in both of them, and they are fairly reasonable. You can read them here, and as it turns out that we are going to have expressions that have delta Z in them for the voltage, and expression that will have delta Z in them for the current, because you have an increment R delta Z here, and the voltage here is in respect to delta Z. So we have to take the limit as delta Z goes to 0 to convert these difference equations into differential equations. So we end up with the following equation here for the voltage right there. Okay, let me highlight that. And we're going to end up with this following equation here for the current. These are simultaneous equations, V here in terms of I and I in terms of V. So we need to get one variable here, plug it into the other one, and reduce them to one variable. As we do that, we have to differentiate. So as we make this substitution between these two simultaneous equations, we end up with a second order differential equation in one variable right here, which is voltage with respect to Z in terms of voltage with respect to time, no more current. Likewise here in the other side, you end up with this kind of an equation here. Now these are voltage expressions. We could have done a similar thing for the current expressions, in which case you will end up with I's instead of V's, but are going to be the same identical equations, by the way. All right. Now how do we solve these equations? The time domain expression here requires going to the Laplace transform to get rid of this partial V partial t. The frequency domain, the differential equation, is more straightforward. As we do a Laplace transform on the time domain, we end up with this expression right here. All right, and guess what? It's identical to the same expression that we had for the frequency domain, and that makes sense because basically the Laplace domain and the frequency domain have similar expressions except for S instead of j omega. The S has a real part, which is sigma, which is useful in solving transient state analysis, while the frequency domain can only be used for harmonic analysis. Now, if we define this quantity here as gamma squared, you end up with this reduced equation, similar thing we're doing here. And the solution is of this form here. What kind of a function that you differentiate twice and end up with the same function multiplied by gamma squared? And that's basically either an exponential or sine or cosine. We use the exponential because it's more convenient and actually covers the sines and cosines. So end up with this expression here. We have two coefficients here. We just named them V plus and V minus for reasons that will be apparent later on. But for now, they're just two arbitrary constants as coefficients of the solution. Likewise here for the frequency domain one. These are similar expressions. We can get the current expressions by going back to the original equations and making some more substitution, and we end up with the current expression. Here it is, current. In the Laplace domain, again, it has the S, and this one has j omega. The coefficient here is the units of inverse impedance, so call it 1 over Z naught. Similar thing here. The thing to notice here is, as a result of this solution, we have a minus sign here as opposed to a plus sign there. All right. So the current expression is similar to the voltage expression except for a minus sign and a coefficient of 1 over impedance there. Okay, now that we have the solution as a function of position, we need to go back now and get the time variation solution. As it turned out that we cannot do that in the general sense easily, so we're going to take a shortcut here, and let's say, why don't we just do it for a simple case of a lossless line, which means R is equal to 0 and G is equal to 0. In this case here, the solution reduces to this form here, which simply says that the voltage and current have a similar form to the original voltage and current, except the time is shifted by a quantity here depending on position. In other words, there will be a delay for the signal to travel down the line. As z increases, obviously the delay is going to increase, and this is a coefficient of delay here, or basically, if you wish, has to do with the velocity of the propagation of the signal down the line. There is a v of t minus and a v of t plus. It looks like we have two different shapes of delays here. This one here is a delay, while this one here is advance. When we explain it later, there's obviously no sense for having an advance. Basically, this one here is the same exact delay, but things are traveling in the opposite direction, and that's why the plus instead of a minus. Okay. Right here is the same thing for a harmonic signal. We can see also again the cosine signal of omega t minus a shift. Here is another shift. Here is the same shift that we are seeing here, in fact, and it's again function of position, linear with position if beta is constant. By the way, alpha and beta were nothing but the real and imaginary parts of the gamma quantity here. We'll explain all that in the next lecture. And the current is similar to the voltage expression, again, with the proper modifier 1 over z naught and the proper change in polarity of the minus sign. Next lecture, we're going to explain the physical insight of all this. What does gamma mean? What does v plus and v minus mean? Alpha and beta, square root of LC, all these constants here are going to make sense to us once we go through the next lecture. We'll stop here. Thank you.